All right, this is the last of our integration videos. This is a U-substitution with a definite integral. And I'm going to show you two different ways. One is the technical method and the other is the sloppy method. They both work really well. So let's try the first one, which is being very, very technical on everything. So we have 2x plus 1 inside of a radical dx. And so we start the same way. We say that's our u. It's normal u substitution. And so our du would equal to 2 dx. And our dx is equal to du over 2. So now plugging that in, we would write this, and we put 0,4, right? Square root of u du over 2. That's not right. See, this is a u now. It's not an x. So you can't use the x values. These are x's. So what do we need to do? We need to come back up here and go, okay, well, x is 0, and x is 4. And you just plug them in for our u. So u is 2 times 0 plus 1, which is 1. And u equals 2 times 4 plus 1, which would be 9. So really we're going from 1 to 9. Now we're done with x forever. No more x. We don't want to go back and look at it anymore. It's all u. These are definite integrals, so we're not getting a number, a function at the very end, an antiderivative. We're getting an area. So we now rewrite it 1 to 9, u to the 1/2. Put a half here, du. Okay, so now we get u to the 3/2, 2/3 times, oops, that's a 1/2. Move that 1 up, it's getting in my way. 1/2, and then we put 9 and 1. So we're going to find an actual answer now. So the 2's cancel. So we end up with 1/3, u to the 3/2, 9 and 1. So this would be 1/3, 9 to the 3/2, minus 1/3, 1 to the 3/2. And that would give us, well, square root of 9 is 3. 3 cubed is 27. 27 divided by 3 is 9. And the next one's nice and quick, 1/3. So this would give us 8 and 2/3. So that would give us 26/3. Now it's nice and quick because we just plug it in the calculator to verify the right answer. And there you have it, 26/3. So that is correct. Now method 2. So method 2 is the sloppy method. It's not technical. And so what we're going to do is basically just say, you know what? No 0, 4. We're going to treat it like a normal integral, a non-definite, and just integrate and find the antiderivative and then plug it in. All right, so you treat it this way. And so we say u equals 2x plus 1. And so du would equal 2 dx. And so dx equals du over 2. And so we end up with the integral square root of u du over 2. And we just keep integrating. We don't worry about those numbers until the very, very end. So we have 1/2 integral u to the 1/2 du. So this again is u to the 3/2, 2/3, 1/2, cancel, cancel, plus c. But you don't write plus c. You just ignore it. So now we say 1/3, and then we replace it with 2x plus 1 to the 3/2, and then now you put them back in, 4, 0. So you're not going to place them back in until the very, very end with the x. So how we're using the U-substitution is to basically just replace the x like before, so it's easy to integrate, and then we put it back in. Once we put it back in, we put in all of the x's. X's go back in at the very, very end. Now when we plug it in, you can see that we're still getting those same numbers. So it doesn't, we're basically plugging in at the end instead of at the beginning. So you can still see that that's 9 and that's 1. So it's going to be the same answer that we get here, which is 26/3. So it's your choice. You can ignore those numbers and not even look at them until you get to the very, very, very end. What I don't want to see, though, is I don't want to see when you've replaced it that you put a 0,4 here, because that is not true. You've got to remember that when we use U-substitution, we are completely getting rid of all of the x's, right? So make sure that your integral is either treated as a normal integral or as a definite integral. But if you replace it, you got to replace all of it. All right, so let's try it again. This time I'm going to do it just the plain old normal way, though. So what's my inside here? It would be this one here, because you can remember that if we take u equals the square root of x, minus 1. This is u equals x to the half minus 1. So my du would be 1/2 x to the negative 1/2 dx. So you can see where it's located, it's on the bottom. So what I'm going to do is just rewrite it as 2u dx over the square root of x, and then that way I can do a direct substitution here instead of rewriting. So this is this. But it's your choice. If you want to always solve for dx and plug it in, that's completely fine as well. So that means the dx, where did the d go? The dx over the square root of x is 2 du. All I did was bring the 2 over, rewrite it. So we now get the integral, and I cannot put 1 and 4 here. So I've got to come back over here and put x equals 1, x equals 4, and then plug them in. So square root of 1 minus 1. Let's put a u so we know where it's going. U equals the square root of 1 minus 1, which is 0. And u equals the square root of 4 minus 1, which is 2 minus 1, which is 1. So we're really going from 0 to 1. So now x is gone. All right? No more x. Don't go back to it. Don't look back to it. It's gone. So now we have u to the 3/2 and then 2 du. So I can bring that 2 out. 0 to 1. U to the 3/2 du. And then we add 1. So u to the 5/2, 2/5 times 2. And we can put 1 and 0. We don't have to go back and deal with anything. So 4/5 u to the 5/2, 1 and 0. So this is 4/5, 1 to the 5/2, minus 4/5, 0 to the 5/2, and that just gives us 4/5. And there you have it. Now we check it with the calculator. And you can see our calculator didn't like this one, but it's still the same answer. It's 0.8 and 0.8. So there you have it. Now if you like the other method, again, you're allowed to use the other method. I am not going to do it again, but it would be the exact same thing. We take the integral, everything would be back here, and you would just have 4/5 square root of x minus 1 inside with the 5/2, and then you would be plugging in the original numbers 1 and 4. But I do prefer this method instead.